In this talk, I will introduce how to evaluate classifier without ground truth label. We usually encounter two stages, training stage and test stage. Given training samples, we train a classifier. Then we evaluate its performance. Given a test image, we pass it through the classifier to get prediction. Then we compare the prediction with ground truth label. If they are same, we say classifier makes the right decision. However, if they are different, then classifier makes the wrong prediction. We usually evaluate a model like this. In the community, we have many well-established benchmarks. For example, we report classification accuracy on ImageNet, evaluate detectors on COCO. In those benchmarks, the ground truth labels are provided. However, when deploying a classifier to real-world scenarios where ground truth labels are not provided, it becomes infeasible to evaluate our classifier. We often meet this issue. For example, evaluating a recognition model on airport, deploying detector to a new city. Without labels, we cannot evaluate our models directly. We need to label data on new testing environments. Note that we need to label again when the test scenario is changed. In this work, we aim to estimate classifier accuracy without any ground truth. This task is difficult, but our solution is very simple and intuitive. Here we have three test sets. They have different domain gaps from training set. For example, the third test set has the largest gap. Let's see the accuracy on each test set. We find that larger domain gap leads to lower accuracy. If we can quantify such relationship, then we can predict accuracy from domain gap. Quantifying relationship is a standard regression task. We first conduct experiment on digit classification. In this figure, each point is a dataset for testing. We use free sheet distance to measure the domain gap. We observe there is a strong negative correlation between free sheet distance and accuracy. On natural image classification, we also have the same observation. This observation makes it feasible to regress classifier accuracy from free sheet distance. Before I introduce our regression models, I would like to clarify some points. We use image transformation to synthesize datasets. Given a seed set, we randomly choose 3 image transformations to change its visual characteristics. In this way, we can generate many sample sets. The labels of each sample set are inherited from seed set. Then we can calculate the accuracy on each sample set. Now, I'm going to introduce our 2 regression models. The first one is linear regression model. This model uses free sheet distance as dataset representation. That is, each dataset is represented as one FD score. We train it on many sample sets and apply it to new test sets. The second method is neural network regression. This model uses 3 statistics to represent each sample set. Specifically, each sample set is represented by its mean covariance and its free sheet distance with training set. We train the network on many sample sets and apply it to new test sets. We have 2 settings. For digit classification, we train a classifier on MNIST and estimate its performance on SVHN and USPS. For natural image classification, we train classifier on COCO and predict its performance on 3 test sets. We first show the estimation of predicted score-based method. When using appropriate threshold, this method can achieve accurate prediction on natural image classification. However, in real-world scenarios, we don't have a chance to select threshold, which means this method is not practical. For linear regression model, it gives good estimation on Pascal and ImageNet. For the network regression model, it gives reasonably accurate estimation on all test sets. Moreover, we add new transformations to create new test sets, and then evaluate our regression models. We show that network regression is more robust than linear regression model. We also try our regression model to predict the accuracy of different classifiers, ResNet, DenseNet, and VGG. We show our methods are effective for them. To conclude, we study an interesting problem, that is evaluating model performance without ground truths. We show that our regression models are simple and effective. We think our method can be extended to other tasks. Note that our models are trained on sample sets. Therefore, those sample sets should be diverse and can cover the distribution of test sets. If not, our model might not work well. Moreover, we use first and second order statistics to represent each dataset. It would be interesting to find other representations. Thank you for listening.